Yeah, welcome after the holidays. This is the first event, first masterclass this year, so exciting. We have Willem from Juniver, who will dive into the technicalities of designing a high-performance SaaS system. It's going to be an interactive session, as Willem told me, so feel free to ask questions. Also, I want to say hi to the people watching us online. Also, feel free to ask questions. We will provide the Slido link in the YouTube comments in a second so that you can ask your questions and Willem will answer them all. During the session, then towards the end of the session, so we want to keep it interactive. So yes, again, welcome and give it up to Willem.
Hello everyone, and thanks for attending. Before we dive in, as has been said, I wanted to try and make it as interactive as possible. So if you have any questions or even remarks, or like, I know some of you have work experience before, like, hey, this was different at where I worked, please feel free to just raise your hand and add in. Let's try not to make this too much like a classroom setting. I know no one likes that here. Yes, so let's first talk about why this topic. I was asked to do a masterclass here. And I thought about it, and when I was in college, I usually just coded, right? And I had a very specific problem that I had to solve. What I liked about when I started working was that you also think about the problems you encounter on a different abstraction level, right? You're not just trying to solve something within a program, but you're trying to actually make the whole system work together. That was something I wasn't really exposed to when I was studying, so I thought it'd be an interesting topic for the masterclass. Before we dive in, maybe a quick word on who we are. I'm saying we, because it's not just me, it's also Jonas, Jelle, and Maarten, who we just hired from Codam, so very, very happy with him, who are here to assist me if I don't know if you're very hard questions. We work at Juniver. It's a fintech startup. The goal is to make, I say the goal because we don't have any product nor customers at the moment. We're very, very new. To make the infrastructure for processing and handling complex payment flows. So it's a payment service provider, like another company here in Amsterdam you might have heard of, Adyen. And what we want to do is allow merchants to monetize payment flows without having to build their own infrastructure. This sounds very complicated, but basically it means, say you have a product, and for example, you're building web shops, and it would be nice if you build a web shop for someone, that if someone does a payment on that web shop, you get a certain percentage of that payment. So you don't have to actually charge them for building the web shop. You can just say, whenever someone pays, I get a little bit of that revenue. That's quite, at the moment, especially as it gets more complex, very difficult to do. That's why we're trying to make it easier for companies. So that's Juniver. Yeah, we're very small right now. So we're on the grachtengordel and we're only with 12 people, if I'm not mistaken. So very small. I'm a backend developer there. Before I spent 5 years at Adyen, which was my first job. I did a lot of different things there. But most relevant for this talk is I was in the scalability team, which was a team responsible for identifying and solving bottlenecks across the Adyen platform. I was also an on-call engineer, so whenever something broke, I was the one that got woken up to try and fix it, or to try and call someone who could fix it. And then I was also involved with trying to move Adyen from a bare metal server setup to more of a private cloud setup. And I wrote some blogs on architecture also for Adyen. Hello. So continuing, what will we talk about? Very high level. I want to cover some. Yeah, I know there's might be some skill difference here, right? So I think it should have something for everyone. I want to first take a bit of the vagueness around it, right? In this space, there are a lot of buzzwords, right? You hear like terms flying around. Some of them mean the same. Some people think they know what something means, but it means completely something else. So let's first go through some high-level concepts. And then I want to kind of work through a system, how you would typically see it. It's very informed by Adyen and a lot of blogs I've read, but I think it translates quite well to other SaaS systems. So you would have first a synchronous layer that's exposed to the outside world, handles requests, then an accounting layer that keeps track of what's actually happening, what's the state of the system, and then the data layer that analyzes that data. So that's how we'll move through it. Along the way, I'll touch upon relevant concepts that might apply across the space, but especially in that area that we're talking about. And this is a bit of a free-for-all. I figured if we have enough time, then we can just have you guys pick what we want to talk about and dive a bit more detail or revisit something we already talked about. And of course, at the end, there will be time for questions. I think I already want to ask, is there any questions now? And what I'm also curious about, is there any things that you hope we will cover? So while you think about that, then I maybe can spend some extra time on that. Maybe good to mention what we won't discuss. We won't discuss things like way of working. When working on distributed systems, we won't go into CI/CD systems. So how do you actually deploy the code you've written? We won't go too much into specific technologies or frameworks. So not why would you choose RabbitMQ or why would you choose Kafka over Pulsar? None of the specific technologies, more what is a streaming framework, right? So just for context. Yes, I will now try to throw this thing.
Oh yeah, it works. So I'm quite curious about the streaming part. I use Kafka for work. I work as a data engineer, so streaming data is part of what I do. And I'm quite curious about how to deal with failures. So fail fast, how do you recover, checkpointing, these kinds of things. That's sort of what I wanted to get out of this.
Nice, thank you. Yeah.
I was wondering about a thing. I'm not totally sure if that's in your level of expertise, but I was also quite interested about how do you actually price a SaaS software or something like that. I don't know if that's something you want to cover today, but I just wanted to ask.
Very interesting as well. That's not really my area of expertise, so I think this talk is mostly technical, but if there's space at the end, we can discuss it, of course.
Cool.
With regards to your point about the streaming, I think we'll cover it mostly high level. Maybe you can say something about it, but since it's really more of a general overview, not really doing a deep dive there. I did work on it a bit at Adyen, and now at June, so yeah, I'll keep it in mind, but I don't think it would be super in-depth.
I'm mostly curious about how do you deal with failures in general, because when you have such a high throughput with transactions, how do you deal with stuff going wrong in an environment like that, where it's everything, like lots going on? How do you deal with failure?
Fair enough. So how to deal with failure in general in a distributed system. That is something that we will cover. And what I try to do is show how the context that you work in determines how you should deal with a failure. And I think that's something interesting, because there's not one specific way to deal with it in every context. Any other points? Or
a small interruption. If you guys want to ask questions, please use the catch box, because like this, the people watching us online can hear us. Otherwise, it's a bit difficult. Thank you.
Yeah, your responsibility is to throw it to the next person. But I don't think there's any other questions at the moment. Also, no questions from online, I see, so then we're moving on. Yes, the magical cloud. So first, maybe on the picture, what I try to do for all the presentations I give is to generate all my pictures. Unfortunately, this was the only slide that produced anything remotely funny. All the others were just garbled text and system diagrams. I guess that's an indication that it's a bit too boring for a dolly, but I couldn't keep this one away from you. What is a cloud? Maybe someone from the audience who has an idea. What do you think of when you think of, because everyone's always talking about it, right? We're deploying to the cloud, but what does it actually mean?
Oh, yeah. AWS. That's
so
the main thing.
Yeah,
I think about.
AWS is a cloud provider, so they run a cloud, maybe here.
Yeah.
It's kind of a quote I keep hearing from other people, but they say the cloud is just someone else's computer.
Yeah, exactly. And to make it even more confusing, you can also run a cloud on your own computer. So, right? Any other ideas? Yeah.
Almost. Well, as I see it, and I think it might be a little bit of a funny thing because you're talking about the cloud. Also on this image, you see a big cloud. But while I think about the cloud, I think about a big data center somewhere, like massive on the ground, and that's the cloud.
Yeah,
yeah,
exactly.
And indeed, you can access it with AWS, Azure, or Google Cloud, or.
Yeah, maybe one final one.
Yeah. So I guess a computer that is, or someone else's computer, but then also, I guess you have access to someone else's computer, but a specific part of that computer, which is managed by another person, so you don't have to do any maintenance, or you have the choice of not doing any maintenance. So like serverless, for example.
Yeah.
So yeah, I think the management part is also very important because or the maintenance part, because it's automatically updated. All these things are taken care of.
Yeah, I think all of them are very valid, right? But it's a vague term. That's why I wanted to spend some attention on it, right? As you can already hear, everyone has kind of this other image of it. It's someone else's computer. It's in a data center. It's managed by someone else. What I think is the revolutionary part about it is that it adds an abstraction layer between the computer you're running something on and the thing you're running, right? And that abstraction layer enables you to outsource, to run something on someone else's computer without too many problems. It enables you to run it in a very big data center where you can do the maintenance very scaled and to outsource the maintenance of those computers. And why is that? Because you don't care about on which computer it's actually running, right? That's the thing you abstracted away. For me, a very helpful analogy here is with shipping containers, right? Why were the shipping containers you see here so revolutionary in shipping is because the person that ships something no longer, like if I want to send something from A to B, I don't have to care how it's transported. And the person that's transporting it doesn't need to care what's being transported, right? Because the shipping container provides an abstraction layer. In the same way, for me, how I think about it, but there's no right answer here, the cloud provides an abstraction layer between the thing you're running and what you're running it on, right? So you can have your own data center and run a private cloud on there. You can have a cloud provider like AWS run it for you and do the maintenance of the service themselves. But you can also run it, yeah. It's more that the quote I like about this is treat your servers like cattle, not like pets. If you have one cow, you will name it and take very good care of it, and then that cow gets sick and you're very sad about that cow and you have to do something else, but you want to treat it like cattle, right? You don't want to care if a server breaks because you want to automatically move the workload to another place. And that's already the second one, right? Because you can scale your workloads very well and you don't have to care anymore about the server that you're running it on. There are some caveats here, of course, but that's the general idea. Is this clear for everyone? All right, great. Moving on. Microservices. I just wanted to put this in here because it was a term that very much confused me when I started, right? What is service-oriented architecture? Why should you use it? And then what's the difference with microservices, another buzzword that you hear? Anyone has an idea about what a service-oriented architecture is?
Yeah.
Maybe application-specific integrated circuits. I don't know.
Yeah, so I think that's on a different level, right? That's more low level. Here, if we're talking about system design, it's really that your architecture, and it's funny because everyone, when we're talking about the cloud, everyone's like, yeah, that's what you have some conception of. I think this is less well known because the opposite of it, which is a monolith, is nowadays not used anymore, right? But a monolith is the natural way to build a system. So before we dive into all these complicated things, right? And as we'll see, we'll add a lot of complication by distributing our system, by making it service-oriented. Where's the name coming from? The name is coming from, it's all built around services. You have a service, you can encapsulate the logic, so the people using it only have to worry about the interface and not how it's implemented.
There we go. Got it. So I guess service-oriented architecture or microservice is more like a version 2.0 of the SOA, in that it just uses more modern techniques like DevOps, I guess, and like you use Kubernetes and failover tooling to make sure that when something goes down, then it automatically goes up again. When you have a new version that needs to be deployed, you have like two versions of the same program. One goes down, the new version gets started, and then the other one goes down, and then you sort of have there's a word for it. But
a lot of people indeed see it as an iteration on service-oriented architecture. There is some confusion. I think, let me first dive into service-oriented architecture a bit more, right? And then I'll spend some time on what the difference with microservice actually is. And I have an example where you can see actually some trade-offs when using like microservices. But the natural way to run a program is just to write a program and run it, right? And you just SSH into a server somewhere, you start your program, you open a port, and then it works, right? You hook up a database to it if you want to be fancy, and then, and then it all runs. But so why would you tear that apart? And then you have to deal with service calls internally, and then and then one part can fail, and then the other part doesn't know about it, and they have to keep working somehow. It's good to realize that you don't have to build a distributed system. That's more what I'm saying. But the advantages are that you can have one part failing and the other part continuing, right? So you could have 3 instances of a program that accepts connections, and then one fails, and the other 2 are still running, so your service doesn't go down. If you have only one program, you can't do that, right? And if we were with a very big team, if we would all work on the same code base, we would all have to understand how all the parts of the code connect to each other. That could get quite confusing quite quickly. So then what we do is we draw lines in the sand between it, and we say, this part of the group is responsible for this service, right? Accepting the request coming from outside. And that part is responsible for actually storing it in the database. So, and you can have agreements on what it should do. So that offers a lot of value. If we take the next iteration on it, we say, okay, but it's service-oriented architecture, but there's still some connections. I want it to be completely independent of each other. So what I'm going to do is we're going to move to microservices. That means make the services smaller, so smaller programs, basically. Again, this is not set in stone, right? But this is how I perceive the current, like the concept as it's currently being used. And what we also do is we say, if a program goes down, it should never impact any of the other programs, right? So you go towards often a more asynchronous way of communication. We'll touch upon that later more. And what you also can do is, let's say we're both the team that's in charge of the incoming connections, changes something in the text parsing library, right? So how strings are converted into JSON, for example, and they introduce a bug, and then something goes wrong in saving to the database because the same library is being reused between teams. So it's still connected. So with microservices, you also try to remove those connections. Famous example of a company that did this to an extreme degree is Amazon. That basically said to every team, you should treat the rest of the company as your customer, right? So you're completely free. Every team within Amazon was, I don't know if it still is, free to choose their own technology, their own tech stack, but they often didn't reuse much of other teams. So the interface they provided, they also had service level agreements and documentation on the APIs they exposed to the other teams. So you encapsulate it, which creates a lot of speed in how quickly you can develop your system, right? But also some overhead because you have to use a lot of technologies. Moving between teams becomes a bit more difficult, and there is some duplication also, and we'll maybe touch upon that later in the type of code you write. Is this clear? Again, this is all, it's not exact science, right? But it's more to give you, once you start working and you hear these terms, that you kind of have an idea like, okay, this is kind of what they're talking about. And again, good to always verify if it's the same thing because a lot of people use these terms in different ways. All right, so now we'll get to the heart of the matter. Metrics, we all love it, right? So when we're designing a system, we can talk about it for ages, but in the end, you're trying to optimize for something. I already alluded that you might try to optimize for different things, but it is always clear to know what you're optimizing for, right? So what are some things that you might want to optimize for when you're building a distributed system? Where is the...
Low downtime.
Low downtime, yeah.
Make it green code, and then less energy usage.
Very good, very good. That's out of scope, but it is a very valid point. I already thought this is very dangerous, yeah.
Number of errors should be low, like failures, but also speed to answer the request.
Yes, speed to answer a question, also called latency. Number of errors was also mentioned there, is I think best described as reliability.
Yeah.
But it also differs, right? So when you use, for example, Twitter, and to see a bunch of tweets on your timelines, yeah, controversial topic nowadays, who would have thought? Or when you use your banking apps, you have different requirements, right? So if you view your Twitter timeline, you might not care that not all tweets are there, right? But if you look at your banking app, you would actually mind quite a lot if not all your statements are there, right? So how would you call the first one? So you look at your Twitter timeline and not all tweets are there. Do we know a term for this?
3 words, you can only choose. There's a theorem, right? That's what you mean?
Yeah, there's a lot of terms about this, right? So especially when you talk about databases and systems, you have a lot of theorems around this that use these metrics and that say that you should only try to optimize for 2 out of 3, for example. But I just put some up here, and let's go through them together, right? So availability, that's the first one. That is really how many times, if I try to call the system, will I get a correct reply? And it's expressed in time. So uptime, basically, is another word for it. And it's usually measured in nines. So it is how many nines of availability do we have? And that's usually connected to a term called service level agreement. So, for example, I run a SaaS system. I have an agreement with my customers that my system will be up 99.99% of the time. So this is referred to as 4 nines availability. Quite high, but yeah, it means that, I don't know, who's good? How many days, hours in a year would this be? Let's see how smart the Codam people are. Yeah, I have no clue. Yeah. But this is how it's usually measured, right? And then we have latency, which was mentioned, right? If I send a request, how quickly should it respond? What I always try to keep in mind here, when I ask myself how important is latency, is the consumer of the API, is it a machine or a human, right? If it's a human, you can care in general less about latency, because a human will not notice the difference between 30 milliseconds or half a second. Maybe that's extreme, but it's not a UI ruining experience. But if a computer is the consumer of the API, then that might actually make a very big difference, right? So can someone give me an example for when latency is an industry where latency is the absolute thing you're trying to optimize for? Yeah, gaming, yes. Trading software, indeed. Self-driving cars. High-frequency trading, yeah. We'll do the next round. We do the microphone again. I appreciated the intention, yes. Yeah, exactly. So those are all things where you're really trying to minimize latency, right? But the design choices that you make on your system really differ when you're trying to optimize for latency. Reliability is very closely related to availability. I always get a bit confused, but it's basically how often you get a wrong response or how often your system goes down. So not so much time, but it's often expressed as a mean time between errors, for example. Yeah, I think that's the term. Mean time between errors. And then consistency. This is the one I was talking about with your banking app, right? A program can be fully consistent and still return errors. It just means that when it returns a response, it is the correct response. Right? And then throughput. So how much data can the system handle? How many requests can it handle before it collapses, basically? If I have to process 1 petabyte of data, how fast could I do it? Yeah.
Scalability, maybe also.
Scalability. And how do you mean? What kind of scalability?
To scale up.
Yeah. So scalability is, how I think about it, is often how far can you push a system until one of these starts to suffer, right? If I do 10x the traffic on my program, will one of these fall between below an acceptable threshold, right? Because it's not, you can't measure scalability, right? That's why I'm not including it as a metric. But in essence, all of these are about scalability, right? So yeah, very good point. Yes. Yeah, maybe try that one.
Maybe it's incorrect. It's around 500 minutes per year.
500 minutes
Something
per year.
Like this, yeah.
Yeah.
And the reliability, how would you test that? So how you actually can test how reliable it is, it also depends on how the users use it, right? So
Yeah,
what would be the test cases to measure reliability?
Yeah, so you have to be able to detect when you actually return an error, right? That's often very difficult with reliability because you can't just say, well, if it's really an error, then it's easy, but if it's incorrect data, then you don't know. But you could just, if you have the live data, you could just get all the requests, right, for example, and if it's just the errors, you can say how many errors there were in that time interval, and then compute the reliability from there. I think the 500 minutes is interesting because if you think about this number intuitively, 4 nines of availability, it seems like very stringent, right? But that means you can have a couple of hours of downtime, a lot of hours of downtime actually in a year, which for some applications is not acceptable, right? So it seems very high, but in essence, a lot of systems go way higher than this, right? All right, let's move on. So keep these in mind when we go through the next parts of the system. The synchronous layer. It's often, I often call it the front end, which is very confusing for people that also work on front end, actual front end. It's not how it looks, but it's more the external facing part of our system. So if a customer connects to my distributed system, they will end up in the synchronous layer, right? So you can think about it. If we draw it, you have here, this is the scary outside world, right? We have a customer, and that makes an API request, and then it will be received by an application, and then all the applications that can receive external traffic are in this layer. Does it make sense? Good.
So then on the right side, you would have sort of the front-facing stuff would be on the boundary. So you would have that sort of square on partly facing. So maybe it's better to visualize it on the where it's both on the left side and on the right side, because like if you've networked it, then all your external stuff is not available. But only that thing can talk to your internal network and to your external network.
Yeah, so indeed you might have a box here. So this would not be possible, but this would be possible. But it could also be that this box is talking to this box, right?
Yeah.
And this is one definition, but you could also say, and that's more alluded to by the term the synchronous layer, everything where the customer expects a synchronous response. Synchronous response is an instantaneous response, right? So in technical terms, if I, for example, do an HTTP request, right, a post, and then I get a HTTP response, that is synchronous. But if I send an email and then later on receive an email, that's asynchronous, right? Or if I do an API request and then later I get a webhook back, that's asynchronous as well. So let's see how we're doing time-wise. So I never did a talk before of 2 hours long. It's such a luxury. I feel like I can talk however long I want. Yeah. So this is what we mentioned, right? Synchronous and asynchronous communication. Let's park these for now, because I think it's better to first go to this one. Because what are we trying to optimize for when we're building the synchronous layer? Usually, it's not universal, but usually.
Latency?
Latency, exactly. And what else?
Maybe throughput, how much can be sent to the synchronous layer?
Throughput, yes, so amount of requests that you could handle per second, for example. Yeah, that's a good one.
Dangerous thing, this. The failure rate.
Yeah, failure rate. I think
if something goes wrong further into the app, you'll want to be able to still show the user an error instead of completely crashing on them.
Yeah, exactly. And it's also I think that's a very valid one, and I think it's also the availability. Because this was, for example, very, very relevant at Adyen, where I worked before. It always had to be available, right? Otherwise people couldn't pay. So it didn't matter if it was slower. So if people wanted to pay and it took, I'm sure you've all been there, it took 20 seconds for actually the approve to show up, wasn't a big deal. But if it says you can't pay, then shop owners would get very, very angry, right? So that was, instead of latency, it was availability. So those are the two things I mentioned here as well. Throughput is interesting because you can actually usually scale this linearly. And I'll talk about this a bit later. That was actually what was on the previous slide. But if you can scale it linearly, it's a very easy way to make sure it can handle all the throughput you need, especially in the cloud where we can scale it dynamically. So what are the strategies for optimizing for these two things, right? I'll talk mostly about availability because latency, it gets very technical, right? It's really fail fast, for example, or writing very fast code, making sure your connections are very fast, and being very diligent on that and add a lot of logging, for example. But in terms of availability, I think the most important one is to eliminate single points of failure. So, and this is the one to keep in mind whenever you're designing something that has to be highly available, eliminate all single points of failure. And that goes throughout the whole stack, right? So a single point of failure means that if that component fails, then the whole system goes down, right? So it could be anything, right? It could be that you just have one application accepting incoming requests, very trivial point of failure. It could be that you have only one internet connection going into your data center. It could be that you only have one data center. It could be that you have a lot of services accepting incoming requests, but they all have a hard dependency on another service that you only have one instance of, right? So whenever you're thinking about this, always also in your code, try to eliminate single points of failure. Because that's killing, right? I usually think of it as kind of like a Swiss cheese model. It's applied to security, but it's like if you have layers of cheese on a sandwich, very Dutch example, I know. If an error goes through this one, it will still keep working, right? It's kind of maybe the reverse, but they all have to align. So, for example, all three services have to crash, and then your system becomes unavailable. So, so that's what you're trying to do. And if you're trying to eliminate single points of failure, what often helps is to make the system stateless. So to have no really long-lived data that's essential for the operation of the system. So a thing that you don't want to do is tightly couple your accounting layer with your front-end layer. We'll go into that later, but say you have incoming requests, right? And it's about users making posts on your self-written social media app. And you want to write these posts to a database, right? If you're optimizing for, let's draw it out. you have a database here. We'll put it in the synchronous layer now. So you have a lot of applications here. And they're all trying to write this to this database. So you get an incoming request, you get a response. These are all serving traffic. And now this database goes down, right? This was a single point of failure because the database goes down. Then this call gives an error, and then you can't return to the customer anymore, right? So you created a single point of failure, the database goes down, you're not available anymore. What you want to do, ideally, is put this, and we'll talk about this more later, put this database here with an application on top, and then, for example, have a queue of items that everyone puts these, puts their messages in. So users make posts. What happens if the database goes down? They're no longer, the queue just gets longer, right? But everything still keeps working. The only thing that happens if then someone refreshes their profile, for example, they don't see the post immediately. But that's an acceptable condition, right? So you see, when you keep these principles in mind and you keep the metrics you're optimizing for in mind, you make different decisions, right? You sacrifice one for the other so that you can optimize for the one you want. And that's what's being mentioned before also. You have these theorems like, okay, you should try to optimize 2 out of 3, for example. So how you design your system, optimize for some and sacrifices others often. Yeah, cap theorem. I think that's, is it for databases? I'm not sure. Yeah. Yeah, that's the one that you want to satisfy all of them.
Yeah. I think it was consistency, availability, and partition tolerance for cap.
Yeah. I'm not sure which context it is anymore. Does anyone know, cap theorem, which context does it pertain to? Well,
I guess it's distributed systems.
yeah, maybe in general. Oh yeah, it's partition tolerances of, yeah, let's try and remember this for the discussion. It comes, it's, I know now. Yeah. But let's not go into it now. Yeah. Any questions maybe first before we move on this one? Synchronous layer. Yes. Yeah.
Can you mention any well-known issues that you can have where you should eliminate the single point of failure, as in like things that can happen very obviously and that everyone who is setting up a system will obviously take into account? Like some common things.
Common things
that you need
for
to handle.
single points of failure in your system.
Yeah.
Yeah, I think it's hard coupling to a database. I think it's just having one instance of an app. Cronus, you know, maybe?
Yeah, single instance.
Sorry, I have to throw this.
No, it's okay.
Yeah.
Okay.
But otherwise the people online can't hear it.
There you go.
No.
Yeah. And I think it's yeah, it's not that clear cut, I think. I think it's also, for example, it could be something, what I often saw is, for example, if you have a memory leak in a front-end application, right? And it's in a library that's shipped to all your applications that are accepting incoming requests. That means that all your applications will have out-of-memory issues, right? So that library is also a single point of failure, in a sense. So you're trying to protect against it by having fail-safes in place that if one part of your program starts consuming a lot of memory, that you box it in somehow, right? So it's not very clear cut, but it's just a principle to keep in mind when you're designing. As soon as you start introducing, for example, service mesh, something we might talk about later, then you also have a single point of failure because everything has to go through it. If you put one proxy for your whole system or one load balancer, basically everywhere where in this part of the system you hear just one, alarm bell should go off. And just check that for yourself. Right? Like data centers are actually very good at this, eliminating them, because they do double, triple everything. It's very nice. But yeah. Yes.
But isn't it like a trade-off decision as well, where when you kind of eliminate one single point of failure, you create a new one, or is there really a way where you just solve all of them and you're free?
If only. If only. Yeah. Yeah, it's not something you can actually solve, I think, in a lot of cases, but it's a risk you minimize, right? Yeah, that's why no one guarantees 100% availability, because a single point of failure that almost all applications nowadays have is the internet, right? And what you saw, for example, is a single point of failure that is acceptable to a lot of companies is for example, Cloudflare, right? Their DNS, I think DNS provider. So when that went down, AWS went down, because Amazon said, we have Cloudflare as a single point of failure, but it's acceptable to us, right? So it's not that it's always bad, it's just something to be aware of. Yes, so the backend. This is, yeah, it's again, when I say I'm working on the backend or the front end of a system, because I'm a backend engineer, I'm always talking about applications and not beautiful looking things. This is, for me, kind of the guts of the system, right? It's where we keep the state of the system. So, again, coming back to our fictive social media app, it's where you keep all the profiles of the users, all their posts, all their messages, all the pictures are all stored here. What I think is nice, jobs and applications. I was confused by this when I started out because I didn't really understand the difference. I think it's quite simple if you know it. Applications are things that can be approached by other processes. So it's things with an API interface, whereas jobs are things that run by themselves. They can consume things from other sources, but they are not approached. And you have continuous jobs, which just run all the time. For example, a consumer of a stream. Or you have one-off jobs. For example, if I need to make a report, I can schedule a job that generates that report and then shuts down again. Just a nice concept to have in mind. Optimizing, so it's the same question as before, right? What are we trying to optimize for in an accounting layer? Yeah, there's a...
Consistency?
Yeah, it's often consistency, indeed. Any other things? Yeah. I think, so you were all correct in not naming another one. I mean, there are other things, right? And again, it really depends on the system you're working on. In general, the main one that comes to mind is consistency. So if you get a response from your, this is really the source of truth often, right? It's also a good sanity check if you're designing a system. What is my source of truth? And if you have two sources of truth in a system, that will almost invariably lead to conflicts between them. And that's very very nasty problem in this distributed systems engineering. So you always want to have one source of truth. So they won't conflict. But if you have that source of truth and you're not getting the answer you expect, then you'd rather have it just fail, right? Instead of just trying something. And this ties in a bit how to deal with failures, right? Whereas in the synchronous layer, you might say, something is not completely going to plan, but I am just going to continue and just do a best effort, kind of. So I'm just going to try and return all the posts for this feed. Or just going to try and gather all the data and send it out and do a best effort approach and continue even though there are errors. If you are optimizing for consistency, you often want to fail fast. So something goes wrong, you can no longer guarantee consistency, you just exit. So you'd rather return an error than something incorrect.
Oh boy.
This is
So, an example of consistency, would that be, let's say you have multiple databases with replication and that they're not all up to date yet. So when you send out the request, you may not know, like the database that you're reaching out to may not have all the data that you, that would be available at that moment, if that makes any sense.
Yes.
Is that part of consistency, that you sort of wait for it to be, for all the databases to be synchronized, and then you return, or you just say, well, I'm just going to reach out, see what's there, and then return?
Yes, exactly. So maybe to illustrate, let's say we have kind of a distributed database system where we have 3 instances of a database, and you have some parts of the data are here, some parts of the data are here, and some parts of the data are here. Or actually, let's say all of them are everywhere. I think that's a better example. So what you might have is an API call coming in and saying, hey, I also want to put this star in. So you add the star to the database, and then another API call comes in, but it hits a different node. And it says, do I have star in my database? Right? If you are optimizing for latency, you will say, no star in the database. But often databases are eventually consistent, as it's called. Maybe, no, that's a step too far. What you could also do is you could ask, do I have star, right, to both of them? And then you would have yes, and then this would instead be yes. If you kind of want to have best of both worlds, what you do is you immediately return no star, but then if you ask later, then you will get a star because they sync internally, but it will just take some time. So you will not have immediate consistency, but you will have eventual consistency. Yes.
Yeah, maybe I missed it, but what was this layer about again?
This is the accounting layer. So this is the layer that keeps the source of truth of your system.
Okay.
So in the case of the social media app, it's all your users, it's all their posts, it's all their pictures. Yeah, and in the case of Adyen, it's basically which payments are done and who owes who money. Yeah, Maarten.
Yeah, so you put the star in one of the databases, right? And it's not synchronized to the other databases.
Yeah.
So what happens if the database that the star is put into goes down before the synchronization happens?
Yes, and this is indeed, I think, where the cap theorem comes in, right? Because now we're talking about partition tolerance. If you want to look into this, I think the most elegant algorithm to solve this is that I know of, that's widely used, is the raft algorithm. So with the raft algorithm, yeah, okay, now I'm going to butcher it, so sorry for anyone who actually knows what it is, but what it does is it's per section of the data, it establishes a leader. So what it does is say this is the leader for the block that would contain stars, right? Because it has all the forms that start with an S. It's a leader for. If this insert comes here, what you would do is you would insert it here. And no, actually, this is not how you do it. What you would do with the raft protocol, forget the leader part, is you insert the star. You say insert star to both of them. As soon as you get one OK back, you know that two nodes have a star in it. And then you return the OK. So now a majority of the nodes has a star in it, right? So if this one goes down, you can still function because you have a majority of the nodes can make decisions for the whole cluster. This is a bit complicated, but there's very nice visualizations on this algorithm. And there's the leader part also plays a role, but it's a bit too much in depth for now. Yes. Do we have the microphone somewhere?
But I'm still a little bit wondering, how does this solve the issue Martin just mentioned? Because now you're like, with the raft algorithm, they're like passing the star on to the others. But what's the difference between that and just the synchronization? Couldn't it be also that the first database goes down before this raft thing has been applied?
Yes, it's a very good intuition. But if this one goes down before it receives the response, it will not say that it actually persisted the star. Okay. Right? It's about the order. So this is 1, this is 2, this is 3, this is 4. If this one goes down before 4 has happened, there is no majority, right? Or rather before 3 has happened or before it's stored, there's no majority, but there's no reply given that the write was successful.
Okay. Yeah. As you, hello?
Yeah.
Okay. As you mentioned that it's essentially responsible for the truth, so to speak, I suppose the priority lies in making sure that you can pull data out of the database, not in latency, right? Because this is essentially going to create a lot of overhead, this algo, right?
This algorithm creates a lot of overhead.
Do you actually need to have all out of the 3 distributed by each other, or you can have 2 out of the 3? So do you need majority when 1 fails, or do you need just majority out of the 3? So do you need 2 or 3? And if
you need 2, because the other scenario. After this, I'm moving on because I could talk for an hour about the raft protocol. But let's say this happens. We have a network failure, and then we get a call, and then we say star. If you just need 1 out of 3, this one could respond no, but it could do so because it doesn't have a majority. Yeah, it's very non-trivial, but there's very nice visualizations. Again, I would recommend you look it up.
Very quickly, I think there's a database called Cassandra. I think they have something built in. If someone is interested in this, because I remember doing something with Cassandra, and there was something about the algorithm you're talking about, and for each partition you would have a leader, and then that one would
almost all distributed databases have this built in.
Yeah.
And that brings us to our next topic, types of databases. These are the main ones, right? You have SQL databases, the ones you're all familiar with, MySQL, Postgres, Oracle, right? And then you have NoSQL databases. Does anyone know the difference between SQL database and a NoSQL database?
SQL database is a relational database.
Yeah.
And NoSQL can store, like an example would be MongoDB, which could store documents, which are essentially JSON blobs. So NoSQL just means, well, with Mongo you can do relationships, but NoSQL essentially just means no relationship by default.
Yeah, so indeed. So with NoSQL databases, you usually just store data blobs. And the schema is often not enforced by the database. I am not an expert on NoSQL databases, so I'm not exactly sure what the state of the art is here. But with SQL databases, you can do joins, for example, easily, right? That's what they're made for. It's like an Excel sheet, you can reference different cells, and that's how we all know a database. But NoSQL databases are very useful for if you want to do point lookups, right? So what it means is you have an ID and you want to have the data belonging to that ID. NoSQL databases, if I'm not mistaken, were made popular by web shops. So for a web shop, what you need, right? You want to surface a page to the consumer with all the different information of that product, right? Who's selling it, the price, the picture, the reviews. If you store all that in a SQL database, you can, but then you have to do an expensive join on it, right? So instead, what you would do is put all of it into one single data blob, because we're optimizing for latency in that case. We put that database in a NoSQL database. We put that data blob in a NoSQL database. You can do point lookups and serve the product pages very, very fast. You can already imagine the problem that arises, right? Because as soon as the information of that product changes, you do have to make sure you update it everywhere. And it's denormalized. Won't go into that term right now, but often it's denormalized, not per se. And then you have distributed databases, which is where you do not have just a single primary when it comes to the database. So that's what you often have with SQL databases. If you're trying to avoid a single point of failure, you have a primary database that services all the requests, but then you want to avoid single points of failure, right? So you don't want, if this one goes down, that the whole system is no longer working. So what you do is you replicate this data to the replicates or the secondary databases. These can also serve read requests, but not write requests. However, you're still capped in terms of scaling the amount of the data in your database by this one instance, right? Because all the data is everywhere. Distributed database, if you go very, very large, you might want to spread that data around. So every node, you have a lot of nodes in your system, and every node only has part of the data. This is again where we get into Raft. I won't go into detail here, but just good to know the differences. And I think as a takeaway, this is the only time I'll actually mention a specific technology. Yeah, just use Postgres. That's really, if there's anything I've learned. Yeah, almost always anything other than Postgres is an overkill. Postgres, I would use Postgres over MySQL because it's really production grade. It's just really, really good. Until a short while ago, Adyen, for example, was completely running on Postgres. Hundreds of terabytes of data, serving synchronous requests. I wouldn't say performing effortlessly, but really doing quite a good job at it. I think it was doing like, you can just bump the hardware and you can really service like thousands and thousands of requests per second. So yeah, that's what I really advise. Otherwise, is this one, right? Really keep in mind, how will you use it? If you're using it to always do point lookups, then you don't need joins, right? So maybe then you want a NoSQL database. But if you would also like to do joins, then definitely don't go for a NoSQL database. So think of the services that are using this database. What processes are pulling information out of it? That's the important part. Any questions on this, except for the Raft protocol?
I have a very risky question. Is the reason you started your own Juniper, I guess, was it called, right?
Yeah, Juniper.
Yeah, is because the Adyen system grew so big and there was no way to change it because it was already so established that you were like, okay, well, we can build a better system because we start from scratch, essentially.
I think even a legacy system can be changed, right? It just requires a lot of effort. It was also mostly personal for me that I joined Adyen when it was 350 people in total, and now it was, I think, 3,000 more when I left. There were very cool projects there, working with a lot of scale, being on call when there's like 1,000 transactions per second going through your system, and you have to have a lot of nines of availability. It's a very cool problem to work on, very intellectually challenging, but it's very different from building something from the ground up and thinking about the architecture yourself instead of tweaking it. And I felt that if I would work at a startup and really also experience that first part of growing a company, that overall it would make me a better developer. Any other questions about, again, we can talk about hours for databases, but I'm just trying to ensure that kind of the basic concepts are clear, right? That when you hear someone say a distributed database, that you kind of know what it means and the type of problem you're trying to solve with it. Because I think that's something to keep in mind. Every tool and every framework and every technology is just a way to solve a specific problem, but you do have to know what problem you're solving yourself and what problem the framework is solving.
What type of database is Postgres?
Postgres is a SQL database.
Not distributed.
Not distributed, yes.
Okay.
Because as I said, like distributed really, maybe I'm missing something here, but for me, it solves a problem of your database not scaling, having too much data in it, basically. And you can partition it, of course. Well, yeah, we'll not go into that, but you can shard it, you can partition it. There's other tricks to do this, but for worry-free, unlimited scaling, distributed database is nicer because you don't have to have all the data everywhere. But there's a lot of trade-offs. And often you can actually just partition the data. Partitioning the data just means you put some data here and you put some data there, and then you say, okay, if I have all the customers with starting with the letter from the first part of the alphabet go in this table, all the others go in that table, I keep this table on that machine, I keep the other table on another machine, and if I query it, I just pretend it's one table and I redirect the query however I want. It also sounds very complicated, but it's actually easy. Safer against what? Oh yeah, maybe repeat it with the microphone. Yeah.
So if you partition, is it like inside one database as one single point of failure still, or is it like two databases and one part you store here and the other one there, meaning that the failure is now half chance, right?
Yeah, so partitioning doesn't really eliminate any points of failure because you don't duplicate data, right? The express purpose of partitioning is to make sure you control the size of the data, of the table. So if you split it, then you will have half of data in one place, half of data in the other. So if anything, it would be less secure because you have two things that can fail, right? But you won't go completely down. So it's not against protecting for that. But it's very good because you're already asking, like, what am I solving with this, right? With partitioning, you're solving growth of the data in the table, not protecting against downtime. But these kind of things, this is exactly how I want you to think when you're thinking about systems engineering, system design. What problems are we solving? What is most important for this? Because you can't optimize for everything. All right, the data layer. This is really almost a separate profession, the data engineer. I won't pretend I am one. I know a little bit about it. Let's say we have a database here, and we have some more databases because we partitioned it. So we have all our data in very neat boxes. This is being distributed however you want, according to the partition, right? And we are very, very happy. And everything is running very, very smoothly. And then an annoying business person comes to us and says, hey, how many posts were there this past week on our platform? You think, how can you ever ask such a question? But your boss tells you have to answer it. So what you do is you need a system that actually brings all of that together again to answer these analytical questions. And that is what we do in the data layer with data engineering. Usually it looks something like this, right? You aggregate it again. And we'll go into the content a bit more. Basically, bring it all together so you can do analysis on it. ETL, something that confused me when I first heard it. It's extract, transform, load. Basically, if you want to do analysis on something, right, you have to have it all in one place and in the right format to run the query that you want to answer. Because you might, for example, want to know how many users from Peru are there. But in your accounting layer, you only store the users with their IP address. So you would extract the layer from your accounting system, then you would transform it by switching the IP address, which is not relevant for the country that it belongs to, and then you would load it into your data warehouse or data lake with that enhanced information. It's a very common pattern to see when it comes to data management. Data lake, data warehouse. Data warehouse is where you run your analytics on. This is, again, very simple in my mind, right? Data lake is just a big dump of all your data, unstructured, unformatted. Stay away from it if you can. This is maybe some data engineers think it's a very challenging problem. Yeah. You have the microphone?
You're partly right, I think. In the data lake, you have raw, defined, curated, or bronze, silver, gold, as in you have your raw where you ingest all your garbage, and then you have an ETL pipeline from raw to silver, and from silver to gold where you slowly increase the value and make aggregations. So I guess data lake is part garbage, part valuable data assets.
Yeah, indeed. So these gold and silver are like standards for the quality of your data. So what you often have is, because you're pulling data from a lot of different sources, you might have incomplete records or null values that are handled differently. So example, empty string, or just null, or just really missing. And as you're trying to enhance it, you go from these different levels, right? If I'm not mistaken. Yeah. And then eventually you get to a standard where you can actually do analysis on it. And these steps are usually done by ETL pipelines. Yes. So what are we trying to optimize for?
Data quality.
Quality, yeah.
Throughput.
Throughput, yes. Exactly. So here you just want to take a lot of data and process it, right? What's often interesting to think about here is whether the data, the insights you gain from it are used real time or just for analysis basis, right? Because what we get when we do it real time, we get something we really don't like. It's quite difficult, actually. We train our machine learning algorithms. For example, we want to know whether shoppers are fraudulent, right? So here we have a lot of data, and we can determine whether shoppers are fraudulent, but we want to use it here to block payments. So we get an error from here to here. So if you're designing a system, this raises alarm bells, right? Because it creates dependencies we don't like. Maybe before we dive into the data layer, I think something we discussed here is worth mentioning again, is this is kind of also a point of failure, right? But it is kind of a way of connecting two systems in a soft way. So this queue, right? Remember, there were incoming requests, we all queued them, all the posts of different users, and then we stored them in the databases. So because we're optimizing for different things in these different parts of the system, here, what we can do is we can say, hey, something has gone wrong. We fail fast, right? Because we want to ensure consistency. What we want to avoid is that spilling over to this side and affecting our availability. So we just say, pause here, this gets longer, we fix the issue, then we start it again, and this layer never notices anything is happening. And I always think about, let's say you have two very expensive machines in a factory, and they're connected to each other with a conveyor belt. You don't want to make this conveyor belt too strong, because then if this machine fails, it will also destroy the other machine, right? So it's fine if this gets long, right? It's fine if this queue goes long. And that's why we don't make it synchronous, because that would be a very strong connection. We will make it a queue, so it's asynchronous. Yeah.
I was wondering, what about latency in this part? I don't know, imagine you have this queue and you have all that data. Does it cost a specific amount of time to actually get all that data as well? I have no idea, or is it like very minimal, or can you just put it aside?
Yeah, it's a very, very good question, right? Because let's say we have 10 petabytes of data here. Latency is a problem there, right? Because you want to get in insights and it takes 2 weeks to process it, then yeah, maybe the insights are outdated already and it doesn't really give you that fast feedback loop. But usually I think about it in terms of throughput, because the result is the latency almost, right? And well, yeah, it is if your ETL pipelines are very slow, right? It might take some time before you get the eventual result. So that's more how fast it goes through the system and ends up maybe in that spot and in the analysis. But I think if that's an hour, it's still fine. But you don't want it to start running behind. And that's more connected to the throughput.
Okay, but like the time involved, so if you go from left to right in this schedule, the last step is not, like it doesn't require a lot of time or anything.
Again, it depends on your use case. I think in general, the results of this analysis are consumed by people. So it doesn't matter if they're an hour old.
Okay.
Right? If you want to gain insight about what kind of shoppers you have, for example, or you do an A/B test on your website to see which layout generates more conversion, it doesn't have to be instant, right? Unless you create this loop in which it becomes more important. Because then here it's consumed by a machine again, by a computer, instead of by a person. Mm-hmm. So I think that's maybe also a factor in it. Is that kind of what you mean, or?
Yeah, well, yeah, so can we conclude that, yes, you need to be sure that is fast enough as well? But, like, yeah, I was wondering, is this handled by the database then? Or can you improve something yourself in your system to get that extraction? Because, well, yeah, I'm sorry, it's getting a little bit confused.
Yeah, it's part, right? It's part handled by the database often. Maybe you have to swap it out for another one, put more hardware in it. It's part by how fast your pipelines are. But the question is more, is it important, right? Before you think, should I try to optimize it? Yeah. Because I sometimes hear, and it's actually a very good point, because I sometimes hear people, data engineers, like bragging, like, yeah, I get my results from my Spark Hadoop cluster with Kafka in between. I get them 50 milliseconds after it happened. Everything's processed. It's like, well, it's great, and they spent a lot of time on it. But why? Why do you need this, right? Mm-hmm. Yeah, it's very fancy, and it's very cool to make it like that. But why do you actually need it within 50 milliseconds?
I guess only in that situation of the alarm bell, right?
Yeah, if it's a really alarm bell or if it's feeding into it and you have to very quickly, if you're training your trading algorithms on it, right, then you want it to be quick probably, something like that. Yeah.
Three questions. So let's say with the first one. So at Adyen, for example, like a payment processor. Yeah. So when you process a payment, then you would probably need, or I've never built anything like that. So if you send a request, do you go through front end, back end, and then when the confirmation, like when the transaction is done in the database, is that when the user gets a confirmation, hey, this has worked? Or do you have something in between that you can make sure that the system knows the payment has been successfully processed, but it's not actually in the database yet? Because otherwise like if you use a queue, for example, then it would be more difficult to get the confirmation back to the user if you have like some...
Yeah, I think you're answering your own question, right? The user gets the confirmation before it's saved to the database, because otherwise you can't both guarantee availability and consistency.
Okay. So for Adyen, like, how would you choose a database for this like data layer optimization? If your use case was to build a payment processor, would you choose, like, how would, like, for example, a transaction or like atomicity, I guess, like an atomic transaction, would that be something you'd take into account, or?
Yeah, well, definitely, right? Because atomicity is that basically any transaction you do against the database, you guarantee that it either completes completely or not at all, right? There's no middle ground there, which is essential. You can't, for example, if you're moving money from one balance to the other, you can't deduct it from the one, and then it fails and you didn't put it in the other, right? That is really what you don't want. So how do you pick a database? Just use Postgres.
Nice. Can I put you in a disclaimer when I tell my boss?
Yeah, yeah, definitely.
Okay.
Yeah, so throughput, also consistency, but that really depends, right? If it's financial reporting, you want consistency. If it's analysis about clicks, you really don't care, right? It doesn't matter if you're, it's about margins, right? If you're off and if you're like a percentage point away, doesn't matter. So you just want to continue, don't fail fast, just give the best possible result. Yeah, I think this is good to realize, okay, you want to pull analysis out of this. How do you do it? How, like, if you think about Hadoop, Kafka, all those like very cool technologies, they usually, what they're very good at is splitting up a question into several subparts, then computing those subparts, and then merging the results to give you the final answer, right? Also, some other very fancy analytical databases do this very well, because it would take a very long time to run analysis on all the data at once, like you would do in a normal transactional database. You have to do a lot of joins. Everyone knows joins are slow, and then you have to compute averages, for example. And just to make it concrete, right? Let's say you have 9 numbers. You can go over all of them, add them up, and then divide it by 9. But if you have a lot of numbers, this will take long. But you can also say, you compute the average of this part, you compute the average of this part, you compute the average of this part, give me the result, add them up, and divide them in 3, right? Very, very simply, this is what these fancy Spark things do, and analytical databases. And they do it very, very well for very complex problems. All right. I think I'm almost done, and we then have half an hour for questions. Yeah, I think this is something I still wanted to mention, event-driven architecture. What is it? It's basically what you, let's say if a user signs up, you want to send an email, right? With the confirmation, hey, welcome to our system. What you could do is you could poll the database every 5 seconds, say, hey, are there any new users? And then the database says no, and then you say again, are there any new users? And then the database says no, you do it again and say yes, oh, great, give me the user, and then you send the email, right? This is a very classical model. However, what you could also do is listen to all the changes in the database, and as soon as a new user is added, only then start doing something. This reduces the chatter, and it's a very popular way of designing a system nowadays to have it event-driven, right? So you don't have continuous polling things, but you have it event-driven. Yeah, and if we do that, then we immediately get to these 3 terms. Queues, streams, and publish and subscribe models. I'm going to create some space here to draw it out. I think a queue is the simplest one, and we shouldn't try to make it more complicated than it is. It's like a queue for a register, right? Everyone stands in line. You might have a lot of registers, and then the queue splits, and you just go to the register, you're being helped, and then you're out of the queue. That's a very simple way to think about it. You can have very complicated, very fast queues as well. But usually it's first come, first serve, order, not super important. And if it's processed, it's forgotten. Then you have a stream. Stream is different in several ways. Yeah, let's first start with the similarities between the two. In both systems, you have kind of a producer or an agent, sometimes called, or there's different terms for it, but something that creates events. And then you have where it's stored, which is the queue or the stream or a topic, which is also a stream, but it's a specific instance of a stream called a topic. And then you have a subscriber or a consumer or a sink. This is also fits very neatly with the ETL pattern we talked about, right? You extract something. Yeah, the transforming and load is here, so it doesn't fit as neatly. But basically, it often does follow this. You extract it, and then you transform it, and you load it somewhere else. In a stream, however, and there's a lot of streaming frameworks, often some state is being kept. So it's not that you process a message and then you forget about it, but you keep the state. And that allows for several things. First of all, you can have several subscribers to the same topic that get all the messages. Right? So you have you could have several processes that are interested in the amount of pictures posted on your social media app. So it's not just one thing that says, oh, a picture was posted and then forgets it, but you can say, okay, how many pictures were posted in the last month, spin up a new consumer, it reads all the history, and then it knows. So you can have that, a lot of them in parallel. What you could also do, which helps with processing a lot of data, maybe you're only interested in a small part of the data. So you're saying, for example, an example from the payments industry would be where you say, okay, I am only interested in the money that is being paid out to this merchant, because I want to make a report for this merchant. So what I do, I listen to the stream of all the money that's being paid out, and I only store it if it has to do with that merchant. So, and then I get a very neat report of all the things that have to do with that merchant, and I can just forget about the rest. And you can have a lot of different consumers that all do the same thing. So at the moment when the merchant wants a report, it's there already processed. Instead of the merchant then having to ask the big database and then having to loop over all the transactions, right? Because that can be very computationally expensive. Yes, where's the microphone?
At what part of the layout will that happen?
It can happen in a lot of places, actually. I think usually, that's why I'm talking about it here, right? It's usually in this part, right? About streaming a lot of data. But what you could also have, for example, is say, again, I'm sorry, but another example from the payments industry, because I think it will make sense to a lot of you. Let's say, we're doing ideal transactions, right? If you do an ideal transaction, you're always redirected to the application of your bank. So you're redirected to the application of your bank, and then you say, okay, you pay, and then before you redirect it back to the website of the merchant, so the merchant knows it was successful, you close the app. So you did pay, but the merchant didn't get a response. What we could do is, for example, we know you paid, so we put all of these things, all of these webhooks, in a stream, or a queue could also work in this case, of course. And then here we have a process that reads from this queue and sends it back to the merchant. Right? So you could also have this system here. And what's nice is, again, if this doesn't work, it doesn't influence this part. Because you don't want to have that blocking connection. But it's a very versatile system. And it can be super, super complicated. But in essence, you just have 3 parts. Somewhere it's stored, somewhere it's produced, somewhere it's consumed. And then you can configure that however you want. And you can also say, I just do round robin. So I have one queue and I have a lot of cash registers, so to speak, a lot of consumers. So when I send out notifications, I just give them to the first one that's available or that takes it. What you could also say is, no, I do want all of the notifications to a certain customer to be sent in order. So I want one consumer to only consume messages, this partition or this key range of the messages in the queue. So you make it sticky. It's perhaps a bit, but you can tweak around with this. That's what I'm trying to say, and tweak it however you want. But it's essential to event-driven architecture, and yeah, it's a pattern you see very, very often. Any other questions on this? Great. I also noticed it's a long session. Huh? Maybe we should have done a break, but it's a bit late for that now. I only now realize. Yeah. Let's see, what is our time? No, let's skip this. Let's skip this for now. I think, yeah, these are the things I want you to take home with you, right? There is no single thing that is the best when you're designing a distributed system. Each part of the system has different requirements, and you should always keep in mind what you're optimizing for and why you're doing it, right? I'm optimizing latency. Is that actually needed? Why am I optimizing for latency? What is the trade-off involved in that, right? These are things that should be kept top of mind. And maybe this is a very much system design way of looking at it. But for me, languages and technologies are just tools to achieve a goal. So you should always check with yourself, is this the right tool for the job? Am I just using it because it's fancy and new? Or is it actually solving what I'm trying to solve? And can I do it in a simpler way? Simpler, always better. All right, and then questions. We already did a lot of questions. I'm very happy. Thanks all, by the way, for how interactive it was. I really liked it. There was a lot of back and forth and a lot of input, so really, really nice. But anything that's still being saved, any questions that didn't really fit into the mix, feel free to ask them now.
So, how is the system you are building different from the one at Adyen?
That's a good question. Good question.
Can you say?
I think it is more event-driven, and that's for sure. I really like it. I really like it. It gives some kind of clarity, right? Because you can really follow an event through the system when you're thinking about it. That's something I really, really like. It's also completely cloud native, which was, I mean, Adyen was founded more than 15 years ago, right? So the world has gone through quite a big change since then. Our system is just fully on Kubernetes, following kind of like the 12-factor app, which is interesting to look at how to develop like cloud-native apps. In terms of system, I think we're not completely following my own advice on always use Postgres for everything, because we are using a different database for our analytics, for example, and just more streaming. I think Adyen also had their queues in Postgres, for example, which was very nice and worked very well. But yeah, it's not very nice to do nowadays because there are just better tools available. So I think it's not the most essential thing is indeed more event-driven, cloud-native, just updated technologies from what was available 15 years ago across the board, I would say. And then I think the most essential differences are really in the business logic that it's able to support, or hopefully sometime in the future might support. Yeah.
Can I have another quick one? Yeah. So, do you have a rule of thumb when it comes to, like, let's say you send a request, how many services can you go through before you go to a response?
Yeah, I don't think I have a rule of thumb for this. I always think just let's keep it as simple as possible, right? If you're doing a lot of service calls, maybe you can cache some things. We didn't really talk about that, but yeah, is it really needed? Can you make some parts of the call asynchronous so it doesn't become a single point of failure? Eliminate it, do it later. I would try to keep everything in the synchronous flow as short as possible. But yeah, maybe that's 2, maybe that's 10. That really depends on the complexity of your business case as well. I would just try to minimize it always. Yeah.
Maybe it's just a personal question. How did you end up working in payments and software? Because I read you studied psychology and physics, if that's correct. Philosophy, that was it, sorry. Yeah. Just curious.
Yeah, that's a personal question. Happy to answer it though. I really like analytical thinking. I just loved it. So when I started studying, I thought, what are the 2 things that have the most complexity? And in my mind, those were theoretical physics and philosophy, which I both really enjoyed. But I also noticed I really like building things. So I really internalize knowledge by applying it, which is notoriously difficult for both of them. So I thought, what is an area where I can actually build stuff, but still have the same complexity and intrinsic complexity in the problems that I'm trying to solve. And that's how I ended up in software engineering. Yeah.
Thank you.
Oh, okay. So is this talk close to what is asked on system design interviews? And if so, like, what are the follow-up materials for this?
I think it's quite close. I think everyone does interview in a different way, but I would, for example, interview people in this way to test how they understand it, right? I don't know, yeah, it's of course very biased, but I think a lot of these concepts, if you can apply them, are quite valuable. What I always like to do in interviews is ask for a design of a system, and then say, okay, but how about you now get 10 times the traffic, right? How would you change the system to deal with that? I think that's always a nice way to think about it, right? You try to run an application or a system and it should be as simple as possible, but then all of a sudden you notice, hey, my response times from the database are getting slower. What do you do, right? Do you then to to follow through how someone is thinking about these questions. A book I really like on this is Designing Data-Intensive Applications from O'Reilly, which is very, just covers these concepts very well. And let's see.
Systems by Codam, that's also a nice one for this type of concept.
Yeah. So distributed systems by Tannenbaum for the people, if there's still people online, then yeah. Yeah, one more question over there. Maybe in 2 hops. Yeah.
I had a question too.
One question in between, great, yeah. Very efficient.
2 actually. But,
yeah, go ahead.
You mentioned, as an example, when a web developer creates a web shop, you want to automate that or make it possible so he gets a cut of when the web shops make some money.
Yeah.
But where does the high performance aspect of what you're focusing on come in? Is it like when company has like shareholders and you want to pay all the shareholders out instantly when the company makes some money or something like that?
Well, that part is not really the high performance. I think in financial industry in general, why I like it, it's maybe the part of the question I didn't answer. I answered why I went into computing science, but not the financial system. The requirements are just very high, right? I think security-wise, availability-wise, and consistency-wise, financial systems just have to be very high level. So, and then the performance is more if, and it's a big if, we should ever be very successful, then you have to deal with a lot of payments, right? Because a payment system is very, very scalable, but that's also its pitfall, right? It needs to have a very large scale to make enough money to justify its existence because it's a very complex piece of engineering.
And can it be done with something like a smart contract?
Yeah, smart contracts. I did some research a long, long time ago into Ethereum. That's what you're referring to?
Not specifically Ethereum, I mean smart contracts in general.
Yeah, so, but you do mean blockchain technologies, right?
Yeah.
Yes. So I always try to think, what is the problem you're solving? I think, yeah, maybe availability and consistency are good on the blockchain, but the blockchain solves one problem very, very well, and that is not having a central authority you can trust. But everyone with a banking card in their wallet trusts their bank. So for the payments industry, this is not really the problem to solve.
Okay.
I was just curious because you said that in 95% of the cases you use Progress SQL.
Yeah, Postgres, yes.
And in what, like, when do you not use it? What?
Yeah, I think the reverse of my advice is online you often read you're not Google, right? But if you are Google or a company of that scale or facing that kind of issues, you should use it. Basically, all the alternatives, they're there for a reason, right? They're there to solve a very, very specific problem very, very well. So if you have that specific problem, and it's different for every technology, right? So, for example, MongoDB serving, or like a NoSQL database, serving large data blobs very, very fast to a lot of clients. Yeah, if you have that problem and you try to solve it with Postgres and it didn't work, then you use it. If you have a lot of data and you can't store it on one node anymore, so that means that you have too much data to store on a disk, for example, or SSD or hard disk, then you might look into a distributed database. If you want to run analysis on your data and it takes too long to do it in Postgres because the joins are too slow, then you might put it in a Spark Hadoop cluster and you run your analytics on that. So it really depends on the type of problem you're solving, which specialized solution you're going to pick. Does it make sense?
Yeah, kind of, yeah.
Any other questions? All right. Well, I want to thank you a lot. My laptop also just perfect timing. I want to thank you a lot. It was a pleasure. I hope this has brought some benefit and kind of cleared up your thinking around what does it actually mean to design a distributed system. Yeah, so thank you very much.